Then let us begin our session. So I will find an interesting problem for you, which is similar to the previous discussion on Riemann integrability. So let us take that f is a function defined on closed interval AB as, let us take the interval as closed interval 1 comma 2, and f of x is equal to 3x plus 1. Now if we do the regular integration procedure, say integral 1 to 2 3x plus 1 dx, can you give me the value after doing the integration as per the usual procedure? Please go for it. Right? So the value is 11 by 2. So everyone accept for this value 11 by 2. Any queries? Right. Now using the technique of Riemann integrability, we are going to obtain the same value. So what we are going to do? We are going to calculate the lower integral as well as upper integral. So first of all, we need to take a partition on the interval. So usually partition will be taken as n parts. H is nothing but the delta R value. The partition will be taken as 1, 1 plus 1 by n, 1 plus 2 by n, 1 plus 3 by n, so on, 1 plus n by n, nothing but 2. So if you take any arbitrary subinterval IR, it will be 1 plus R minus 1 by n, comma 1 plus R by n. So rth interval will be written like this, and this is the length of the rth subinterval, and this is the partition we have considered. Now if you observe the function 3x plus 1, is it increasing 1 or decreasing 1? If you substitute the values one after the other from 1 to 2. So whenever you take a subinterval, the first point will give infimum value of the function over the interval, and the last end point will give supremum value of the function over the subinterval. So if you take small mr is equal to infimum of the function on the subinterval IR, it is nothing but f of 1 plus R minus 1 by n. So you are substituting the first point in the given function. So it is nothing but 3 into 1 plus R minus 1 by n plus 1. That will be the value. So if you simplify the value, it is nothing but 4 plus 3 by n into R minus 1. So similarly, if you calculate the supremum of the function on the subinterval IR, it is given by the last end point. So f of 1 plus R by n. So this is equal to 3 into 1 plus R by n plus 1. So this is equal to 4 plus 3R by n. Accepted? Now I am going to calculate the lower sum as well as upper sum over this interval. Then if I apply limit n tends to infinity, then I am going to calculate the lower integral as well as upper integral from the lower sums and also upper sums. So if you consider the upper sum, it is nothing but UPF is equal to summation R is equal to 1 to n mr delta r. This equal to summation r is equal to 1 to n. Mr means 4 plus 3r by n. Delta r is nothing but 1 by n. So if you separate the values there, you are going to get it as summation r is equal to 1 to n 4 by n plus summation r is equal to 1 to n 3r by n square. Since r is the term which is varying here, so 4 by n is constant here, 3 by n square is constant here. So separating the summation r is equal to 1 to n 1, 4 by n is a constant, plus 3 by n square into summation r is equal to 1 to n r. So if you expand it, it is equals to 4 by n into, you are adding 1 n times, so it will be n, plus 3 by n square into, it is nothing but sum of the first n natural numbers, so n into n plus 1 by 2. So n gets cancelled here, it will be equal to 4 plus, taking n as common here, n square gets cancelled, so 3 by 2 into 1 plus 1 by n. So please check on this value. Any questions on this? Right. Now to get the upper integral, that is integral 1 to 2 bar f of x dx is equal to limit n tends to infinity UPF. So if you apply limit n tends to infinity for the upper sum value, it is nothing but 4 plus 3 by 2 is equal to 11 by 2. Similarly, you can calculate LPF value, summation r is equal to 1 to n small mr delta r. The same things will go on to apply here. Here you will get n into n minus 1 by 2. So 4 plus 3 by 2 into 1 minus 1 by n you will get. And at the end, the same answer 11 by 2 will come if you calculate the lower integral. So lower sum and upper sum are almost equal. Only the symbol will vary there. Here you will get 4 plus 3 by 2 into 1 plus 1 by n. In lower sum you will get 4 plus 3 by 2 into 1 minus 1 by n. That is the only modification. And limit value will give the same number 11 by 2 and 11 by 2. So lower integral and upper integral both are equal. Hence the function is Riemann integrable. Therefore the common value 11 by 2 is nothing but the integration value over the interval for 3x plus 1. Okay. Any more questions on this? Please ask. Then I will take the other one. Yes or no? So please take a note of it, then we will go for the other problem. So I have skipped the part of calculating LPF and applying limit n tends to infinity. Is it required for you to find LPF also? Right. If it is required, I will write it on board again. Anybody requires that, finding LPF? Okay. Now let us take the similar kind of problem. So you take closed interval 0 comma pi by 2 and take the function f of x is equal to sin x. So using the same technique, you are going to show that the function is Riemann integrable, calculating lower integral as well as upper integral, and we are going to find the integration value. So if you want to find the delta r, it is nothing but b minus a by n. You are making the n equal segments in the partition. It is nothing but pi by 2 minus 0 by n equal to pi by 2n. And how the partition looks like? The partition P is equal to 0, pi by 2n, 2 pi by 2n, and so on, pi by 2n, pi by 2. So if you write arbitrary subinterval IR, it will be r minus 1 into pi by 2n, comma r pi by 2n. It was the rth subinterval. Please check on that. Any more doubts over the partition, interval length and rth subinterval, you can ask. Because this is the usual way in writing the partition, writing rth subinterval and the length of the subinterval. Right. Now you can calculate the UPF as well as LPF. Now the question here is, if you consider sin x function on the given interval, is it increasing or decreasing? Sin 0, sin 30, sin 45, so on, sin 90. Increasing. So obviously, whenever you take a subinterval here, since the function is increasing on the subinterval, here the first one gives the infimum and this one gives the supremum. So, supremum mr is equal to sin r pi by 2n, infimum small mr is equal to sin of r minus 1 into pi by 2n. And length of the subinterval is nothing but delta r pi by 2n. Now you are going to calculate UPF as well as LPF, anything you can take. Suppose you have taken UPF. So this is nothing but summation r is equal to 1 to n mr delta r. So this is equal to summation r is equal to 1 to n sin r pi by 2n into delta r means pi by 2n. Since r is the varying parameter here and pi by 2n is constant, you can take pi by 2n to the outside. So this is equal to pi by 2n into, expanding the summation, it will be sin pi by 2n plus sin 2 pi by 2n plus so on plus sin n pi by 2n, nothing but sin pi by 2. Or sin n pi by 2n you can write like this. Now, how to simplify this summation of terms? Do you know any formula regarding that? They are in the arithmetic progression. You can say they are of the form sin A plus sin of A plus D plus sin of A plus 2D plus so on plus sin of A plus n minus 1 into D. So do you know any kind of problem related to this with regard to trigonometry? Yes or no? So if it is not known to you, then the formula will be like this: sin of A plus n minus 1 by 2 into D into sin n by 2D or sin nd by 2 whole divided by sin d by 2. This was the formula. You can take sin nd by 2 whole by sin d by 2. So please take a note of this. Then you are going to substitute the values here. So here d is nothing but pi by 2n. A is nothing but the first term sin pi by 2n. Okay. After noting, please tell I am going to substitute the values there by erasing this part. Any more questions with regard to the calculation of UPF so far? Fine. So after noting, you please tell I will go with the substitution in the formula. So if you substitute the values there, so it will be sin of A means pi by 2n plus n minus 1 by 2 into D means pi by 2n into sine n by 2 into pi by 2n whole divided by sine pi by 4n. This is the value using this formula. So here n gets cancelled and sine pi by 4 is nothing but 1 by root 2, and in UPF earlier you have pi by 2n because pi by 2n into something. For that something summation you have calculated the thing. Since sine pi by 4 is nothing but 1 by root 2, taking this value here, it will be pi by 2 root 2n into sine of can you tell me the value by taking LCM here for the two terms there? Is it n plus 1 of pi by 4n, nothing but sine n pi plus pi by 4n? Or you can say like this. Please check on the value. After taking confirmation from you, then I will continue. All of you agree for that value? Right. So in the numerator, if you apply the technique sin of a plus b, like sin a cos b plus cos a sin b, it is nothing but pi by 2 root 2n into sin pi by 4 into cos pi by 4n plus cos pi by 4 into sin pi by 4n whole divided by sin pi by 4n. Now what happens? Either sin pi by 4 or cos pi by 4 is nothing but 1 by root 2. Taking this value here, it will be pi by 4n, the front side. And for the rest of the part, it will be pi by 4n into. So cos by sin is nothing but cot pi by 4n, and it is nothing but 1. Sin pi by 4n plus sin pi by 4n by sin pi by 4n, nothing but 1. So this is the value of UPF, and now you are going to apply limit n tends to infinity for this one. So you can write it as multiplying with this one as pi by 4n plus pi by 4n by tan pi by 4n. You can write like this also. And for this value, you are applying limit n tends to infinity because the upper integral 0 to pi by 2 par f of x dx is nothing but limit n tends to infinity UPF. You please check on that. So if you apply the limit, as we know, you have a formula that limit theta tends to 0, tan theta by theta is equal to 1. So using this kind of formula, the value is nothing but 1. If you apply limit n tends to infinity UPF. So on checking that, you tell yes or no. How to calculate the upper integral. If everyone agrees with that, then we will go with the lower integral part. I think this kind of problem is given earlier in the previous year questions in UPSC. Any questions on the limit part? Please tell. So if you apply limit n tends to infinity, the upper interval is nothing but 1. Accepted? Similarly, if you calculate the lower integral, the same steps will come, the same formula you are going to use. At the simplification part, you will get pi by 4n into cot pi by 4n minus 1. So here you have to think like this. A symbol will vary here. That is the only thing you are going to get. So here you will get minus pi by 4n plus pi by 4n by tan pi by 4n you will get if you calculate LPF. So since the space is conservative among LPF and UPF, we just calculate only one value. For the other, similarly you are going to have LPF value like this. We will write like that. We don't calculate the other sum. So calculation of one sum is enough because the problem becomes very lengthy after doing all these parts. Okay? Accepted. So in the examination, we just calculate only UPF and calculate the upper integral. For finding LPF, without doing this simplification part, straight away we mentioned that LPF is equal to pi by 4n into cot pi by 4n minus 1 we will write. And limit we will apply, that's all. So lower integral is equal to 1 and upper integral is equal to 1, hence the function is Riemann integrable. So integral 0 to pi by 2 sin x dx is nothing but 1. That was the answer. Clear? Right. Now, if similar kind of problem is given on cos x, so if you take the interval as 0 comma pi by 4 and the function is cos x, using the technique of Riemann integrability, prove that it is Riemann integrable and find the integration value, what it will be, the value. Or is it integrable or not, you are going to find it. That you can take it as an assignment. So you take it as an assignment and I will give the formula for calculation purpose which will be useful to you. So this is the formula while simplifying the summation. You please take a note of it. The formula for simplifying the summation. So you can calculate UPF and LPF as well. You can take it as a practice on your side. And I will go for the other conceptual problems. So let us take one previous year question problem. Just hold on a moment. So the question is given as, suppose on closure interval 0, 2, the function f of x is defined by x plus x square and x square plus x cube. If x is rational, if x is irrational. This is the problem given. It is also one of the previous year questions in UPSC. So how the question is framed? On closure interval 0, 2, f of x is defined as, whenever you take a rational number, the function value is x plus x square. Whenever you take an irrational number, its value is x square plus x cube. Now the question is, using the technique of UPF and LPF as well, you are going to verify whether the function is Riemann integrable or not. Okay? That was the question. Is it clear? So please take a note of it and we will discuss on it. Now what happens if you consider closure interval 0, 2? So you can take x between 0 and 1 and you can take x between 1 and 2. Why I am choosing like this? Because if you take x from 0 to 2, any value among x plus x square and x square plus x cube, which one is big and which one is small? Why I am bothering about this? Because if you want to calculate UPF or the upper integral, if you want to calculate LPF or lower integral, you should know which function gives UPF and which function gives LPF, isn't it? You should know what is the infimum and supremum for the interval. Yes or no? Because for every interval, whenever you consider, we are discussing about small mr and capital MR, which is infimum and supremum of the function over the subinterval. So for this, what I am doing here is, you simply consider the difference of these two. So it is nothing but x minus x cube. If you common x here, it will be 1 minus x square. Now what happens if you take x from 0 to 1, that means in between 0 and 1, let us say. Now what will be this portion 1 minus x square? Is it positive or negative? If you take x between 0 and 1, what about 1 minus x? Is it positive or negative? Try with a number. Positive. So in other words, the difference between these two is greater than 0. In other words, this part is bigger than this part. Accepted? X plus x square is greater than x square plus x cube. Agreed, all of you. So this is the big one and this is the small one. So this part gives the supremum and this part gives the infimum. Right. Now whenever you take x which is bigger than 1 and smaller than 2 in this portion, if you consider 1 minus x square part, it will be negative. Accepted? If you take 1.5, so 1 minus x square will be obviously negative. So what happens? X plus x square is less than x square plus x cube. So this is the big one and this is the small one. So this gives infimum and this gives supremum over this interval. So far, whatever the problem we have done, we have calculated by taking a partition P, taking subinterval length delta R, having the sums UPF, LPF, and we have calculated limit n tends to infinity. But for this problem, we simply bifurcate the total interval as integral 0 to 2 is equal to integral 0 to 1 plus integral 1 to 2. And we simply integrate the values. So if you want to find the upper integral, we take the supremum, which is given by the two functions over the interval, and integrate. If you want to calculate the lower integral, so we take the infimum from taking the partition and applying limit n tends to infinity. This was the technique we use in this problem. So it is a slight variation compared to the previous one. However, if you are interested, for each subinterval 0, 1 and 1 to 2, you can take a partition and you can calculate LPF and UPF as well. That is up to you. But this is the technique that based on the previous result, we simply bifurcate the interval and we simply do the regular integration. So what we are going to do is, if you want to calculate the upper integral, integral 0 to 2 bar f of x dx, we are calculating the upper integral by taking the upper function. So integral 0 to 1 plus integral 1 to 2. Here I am taking the upper function. What upper function? On the first one, which one is infimum and which one is supremum? So this one is supremum and the previous one is infimum. So it is nothing but integral 0 to 1 x plus x square dx. On the second one, 1 to 2, x square plus x cube will be the supremum. This one we will find by doing the regular integration. You please check on that. So if you want the lower integral, integral 0 bar to 2 f of x dx, so you are taking the lower integral, integral 0 to 1 plus integral 1 to 2. So in integral 0 to 1, the lower part is given by x square plus x cube. From 1 to 2, the lower part is given by x plus x square dx. Now you are going to calculate the two integration values and you can tell me what are the values here. So this problem is somewhat different compared to the previous examples. I will say that one part you will get the value as 83 by 12 and for the other part you will get the value as 53 by 12. So lower integral will be 53 by 12 and upper integral will be 83 by 12. So by doing the simple integration, you check and confirm the answers. So here we are not considering any partition, please understand. We are simply taking the function values which is giving infimum and which is giving supremum over the bifurcated subintervals and we are simply integrating that, that's all. And it is one of the previous year questions. Now what happens? The upper integral is 83 by 12, lower integral is 53 by 12, both the values are unequal. Hence, the function is not Riemann integrable. That was the conclusion. Okay. If everyone is clear with the calculation, then I will take the other problem. So there is one problem which is also given the previous year papers. The interval is given as 0, pi by 4 and the function is defined as f of x is equal to cos x and sin x if x is rational, if x is irrational. Now you are going to verify whether it is Riemann integrable or not. As usual, we will take a partition. We calculate UPF, LPF, simply apply the limits. So, I will give it as exercise for you, and I will post the solution in Telegram group. You can check it because it is very easy. There is no special concept here. Simply the simplification part is necessary for you. I will give the posters in Telegram group. You can check for it. Okay. With regard to this problem. If you have more confusion after seeing the problem, then I will take the class session on it. So please take a note of the problem. The interval is given as 0, pi by 4, and the function is defined as cos x and sin x if x is rational and if x is irrational. And you are going to verify whether it is Riemann integrable or not. Clear? So after the completion of class, I will give a posters in Telegram. You can check for that. And you can practice on your own if you have still confusion over it. Now, the another problem is, it is also similar to the previous problem what we have discussed. So you take the interval as closed interval 0, 1, and the function is defined as f of x is equal to root of 1 minus x square if x is rational, and f of x is equal to 1 minus x if x is irrational. And we are going to verify whether the function is Riemann integrable on this interval or not. It is very similar to the previous problem what we have discussed, x plus x square and x square plus x cube problem. So among the two functions which are given there, which function is giving infimum and which function is giving supremum to us must be known to us. Then we simply integrate those values over the interval because it is simply one interval 0, 1. It is not a big interval to bifurcate the function values. Now how to know that which function is big and which function is small among the two? Any guesses? Among root of 1 minus x square and 1 minus x, if you take any x value on 0, 1, which one gives big and which one gives small? Right. So I will say that, so if you take the function 1 minus x square, you are going to write it as 1 minus x into 1 plus x. Accept it? Right. So we have 1 plus x is greater than 1 minus x. So here you can say this will be greater than 1 minus x into 1 minus x. Agreed? So what happens? We have 1 minus x square is greater than 1 minus x whole square. So if you take square root on both sides, root of 1 minus x square is greater than 1 minus x. Accepted all? For 0 less than x less than 1, please understand here the case. Yes or no? Therefore, what happens among the two functions? First one gives the big value compared to the second one. So this is nothing but the supremum and this is nothing but the infimum. Clear? So if you want to calculate the upper integral as well as lower integral, for upper integral we will do that. Integral 0 to 1 bar f of x dx, the upper integral is nothing but integral 0 to 1 root of 1 minus x square dx. For this you have a straightaway formula, integral square root of a square minus x square. You have a formula there. I will say it will be x by 2 into root of 1 minus x square plus 1 by 2 into sine inverse x between the limits 0 to 1. Can you remember that formula? So if you apply the limits there, on applying the limits, you will get the value as pi by 4. Can you check on that? The limit part, substituting the values. Similarly, if you go for the lower integral, integral 0 bar to 1 f of x dx, it is nothing but integral 0 to 1 minus x dx. So if you do the simple integration here, integration for 1 is x, integration for x is x square by 2. If you apply the limits, the value is nothing but 1 by 2. Please check on that. So the lower integral and upper integral, both the values are unequal, hence the function is not Riemann integrable. So far, if you compare the previous class discussion and today's class discussion, what we did, whenever the function is straightaway given clear and the interval is partition friendly, then we will take the partition, calculate UPF and LPF, we will apply the limit and we check for that whether the lower integral and upper integral both are equivalent or not. That is one way of doing the problems. The other way here is, whenever the function is given like this, like rational, irrational, etc. Now what we are doing, in order to calculate the lower integral and upper integral, we simply compare that which function is giving upper sum, which function is giving lower sum on the whole interval or the subinterval, whatever the case may be. And by simply taking the function and integrating that over the interval, you will get the lower integral value as well as the upper integral value. That is the whole idea behind the problem solving session. Okay? Any more clarity you require more than this? You please tell. So if you want to take a partition for this kind of problem, let us take a similar kind of problem on this. Shall I arrange this problem? All of you have noted? Because you can find LPF and UPF as well. There is no problem at all. Now see, let us do the case here. So you are going to take first of all, you need to take a partition on it. Accept it by taking the partition. Delta R is equal to 1 by n and P is the partition taken like this, dividing the range into n parts. Accept it? Fine. Now what happens, if you want to find LPF, it is nothing but summation R is equal to 1 to n mr delta R. So summation R is equal to 1 to n, delta R is nothing but 1 by n. Now the question is, what is uniform here? You are going to write what is the function value here, isn't it? Since whatever the subinterval you consider, if you take any segment from 0 to 1, whatever the small segment you consider, obviously it will contain so many rationals as well as irrationals. Accept it? You can choose any kind of endpoint there, interval endpoint. Yes or no? Interval endpoints may be rational or irrational, but whatever the interval you consider, it will contain so many rationals as well as irrational numbers. Since the function is bifurcated as rational and irrational, so one of these values will give the infimum and supremum. So the thing is nothing but among the two functions, which one is big and which one is small is known to you. That is nothing but infimum and supremum you have considered. So as the case you have taken, so if you write the function is 1 minus x square, so what will be the interval here? So it will be r minus 1 by n into r by n, the interval or subinterval if you will write. Since this function is big and this function is small, so for LPF we need to consider this function. Again you have a doubt here. So if you take the function 1 minus x, among these two things, which one is big, which one is small, you are going to mention, isn't it? Because if you take r minus 1 by n and r by n, for 1 minus x, which one is giving the infimum and which one is giving the supremum? Again you have a strucking condition there. You need to think, because n is arbitrary there. You cannot define n there. So to avoid that confusion, we are simply checking for the function which is big and which is small, and straight away we will calculate the integration value. That was the technique here. It is a method described as per a procedure. So apart from the regular programs, it is somewhat different. That's why I have chosen that. So again you can do that for r minus 1 by n and r by n, whatever the number it may be. So you can take any endpoint, because the infimum and supremum are not based on the interval endpoints, they are based on the function values. Because r minus 1 by n may be rational or irrational, whatever the case may be. So here the infimum and supremum are not based on the endpoint, they are based on the function values. Suppose you have taken r by n, right? Let us fix the point r by n. So what will be mr here? 1 minus r by n. Since the function is 1 minus x, it is giving the infimum. So here you are going to take it as 1 minus r by n into 1 by n. So you will get it as summation r is equal to 1 to n, 1 by n minus r by n square. So if you separate the values, you are going to get it as, so here 1 by n into summation r is equal to 1 to n 1 minus 1 by n square into summation r is equal to 1 to n r. This will be 1 by n into n minus 1 by n square into sum of the first natural numbers, so n into n plus 1 by 2. So we are going to get it as it is 1 minus 1 plus 1 by 2 into 1 plus 1 by n. So it is nothing but if you apply limit n tends to infinity, 1 minus 1 by 2, the value will be 1 by 2. You can check on that. If you remember the previous problem, the function is given as 3x plus 1 and the interval is taken as 1 plus r minus 1 by n comma 1 plus r by n. So you are taking one endpoint here and substituting in the function, which is nothing but infimum and supremum. So here you can write mr and mr as functions of x. So if you write functions of x, there is no need of writing limit n tends to infinity. Straight away we are doing integration. So small mr is nothing but 1 minus x, capital mr is equal to root of 1 minus x square. That is exactly correct. So we are simply finding among the two functions which is infimum and which is supremum, or the interval you have considered. Since it is a single interval, there is no need of bifurcation. If you take closed interval 0 comma 2, then you need to figure out which function is giving supremum and which function is giving infimum over the intervals 0 1 and 1 2. Okay, and we will integrate accordingly. Is the ideology clear? You can take partition also. By taking partition, writing small mr here, you can apply limit n tends to infinity. So that you will get 1 minus 1 by 2, the value is 1 by 2. This is the calculation for LPF. Because it is a tedious procedure. So apart from doing like this, straight away write mr and mr as functions of x and do the integration. That technique usually we will do whenever a bifurcation of interval is there. So 1 minus x is an increasing function in the given interval. Please understand, you can take the first point as well as, see, in the interval, what can we say about the end point? Because there are two functions, 1 minus x and root of 1 minus x square. The x, what you are choosing may be rational as irrational. Anything you can take, right? Corresponding function will vary. Sometimes 1 minus x value will be big compared to root of 1 minus x square depending upon the x. On the interval what you have chosen. So the end points, we are neglecting that, we are only focusing on the function. That's why we are simply integrating the function. So on 0, 1, can you say that 1 minus x is increasing function? As x value increases, 1 minus x decreases or increases? So it is not an increasing function. Right. Increasing function. Clear. I think it gives the clarity over the problem. Any more doubts for anyone? Yes. In any interval, the function is not unique. We are not, because if there is only one function like x square, x cube, 3x plus 1, 1 by x, etc., then obviously, since there is only one function, by observing the nature of the function over the interval, straight away we can define that on this subinterval, this is infimum and this is supremum in the endpoints. Since the function is not unique, because function is assuming two values, root of 1 minus x square is one value and 1 minus x is other value. The only thing you are going to find is, since it is taking rational and irrational values, which function is giving infimum and which function is giving supremum. That is the whole thing we are bothering. That's all. Okay? So in any subinterval, the function is not unique. It will assume two values. Just like the case of the previous problem, cos x and sin x. When x is rational, the value is cos x. When x is irrational, the value is sin x. So if you take any subinterval, then the function is not unique. So depending upon the two, cos x and sin x, which is giving big value is supremum, which is giving small value is infimum. That's all. Is the ideology clear? You can apply by taking a partition and limit n tends to infinity. And you can find the lower and upper integrals, no doubt at all. So the question what you have asked, after seeing the posters, after the completion of class, you will have the clarity. I will give the posters after the class. Now let us have some small discussion. Earlier we did a problem that in the previous class we have done this problem. Say yes or no. And it is not Riemann integrable, right? On closed interval AB, the function f of x is defined as 1 and minus 1. When x is rational, the value is 1, and when x is irrational, the value is minus 1. And it is not Riemann integrable, because one value you are going to get it as b minus a, and one value you are going to get it as a minus b. Since the values are unequal, it is not Riemann integrable. Now, what can we say about the modulus of f of x? It is nothing but the constant function 1. Accepted? Yes or no? If you consider modulus for this function. Since the constant function is integrable, so here what you can say, here mod f is integrable, but f is not integrable. So this kind of problem we can take as an example for, give an example that the function is not integrable, but modulus of the function is integrable. This is the example you can take. Any more doubts? Right. You can take a similar example that, let us say, you take f of x is equal to 0 and 1. Say if x is rational and x is irrational. Now, if you write a partition, so you can take the closed interval AB as well. Any closed interval AB you can take. The function is defined like this. When x is rational, its value is 0. When x is irrational, its value is 1. So what happens? Whatever the partition you take, A is equal to x0, x1, x2, so on, xn is equal to b. If you take any subinterval IR, x r minus 1 comma xr, the subinterval length is delta r. You can calculate LPF as well as UPF. So if you observe that the maximum value possessed by the function is nothing but 1 and the minimum value possessed by the function is nothing but 0. What are the partition you take, what are the subinterval you consider, and what are the endpoints and intermediate values in the interval. The maximum value for the function is nothing but 0 and the minimum value for the function is nothing but 1. So supremum is nothing but 1 and infimum is nothing but 0. So if you calculate UPF and LPF as well, it is going to come as, so if you write LPF, summation r is equal to 1 to n mr delta r, this is equal to summation r is equal to 1 to n 0, delta r value is 1 by n because you are taking n parts, it is nothing but 0. So if you apply, if you calculate the lower integral a bar to bf is nothing but limit n tends to infinity LPF, it is nothing but 0. So if you calculate UPF, summation r is equal to 1 to n capital mr delta r, since the supremum is 1, it is nothing but summation r is equal to 1 to n 1 into delta r. You are adding all the lengths of the subintervals, it is nothing but b minus a. So if you calculate the upper integral a to b bar f, it is nothing but value b minus a, limit n tends to infinity UPF value. So LPF value and lower integral value is nothing but 0 and upper integral value is nothing but b minus a. Since the values are unequal, the function is not Riemann integrable. Why I have taken this discussion? Because this function is a good example that it is a bounded function. Accepted? Because the function possesses infimum and supremum. The infimum of the function is 0 and supremum of the function is 1. It is a bounded function. As and when we talk about the concept of Riemann integrability and the definition of Riemann integrability, we always talk that if whenever you take a bounded function and if you calculate lower and upper integrals, if they are equal, it is Riemann integrable. We always say like that. So now the question arises that is every bounded function is Riemann integrable? It is a question for us. So here the example says that it is a bounded function because infimum and supremum are existed for the function, but the function is not Riemann integrable. In the previous case also you can take 1 and minus 1. It is also a bounded function. That example also you can take. It is another example. So every bounded function need not be Riemann integrable. It was the question. Okay. Modulus of every bounded function is Riemann integrable. That's a good thing. Now let us say, if you take modulus of a function, let us say mod x on closed interval minus 1 comma 1. Can you check on that by taking a partition? Is that Riemann integrable? Now the question comes like that. So one assumption is, if you say that mod x is a continuous function, right? As we have discussed an important result that every continuous function is Riemann integrable. So always it is Riemann integrable. So in that point of view, we can say that modulus of every bounded function is Riemann integrable. That we can say. Okay. I will find a good example for you for the discussion. The doubt you have asked. I will fetch for that if possible right now. So since the modulus of a function is always continuous, if that is true, then every continuous function is Riemann integrable. Therefore, modulus of every bounded function is Riemann integrable. We can say like that. So here, yes, that is what I am saying, because we have different results. If you define the function like that, is it continuous function? 0 and 1 if you define like that? We have done similar kind of problem. If f of x is defined like that, is it a continuous function or not? Can you remember the sequence criteria of continuous functions? We have discussed it a long back. So by using sequence criteria, if it is continuous, fine, it is Riemann integrable. If it is not continuous, please understand that continuity is not a necessary condition for Riemann integrability. Discontinuous functions are also Riemann integrable, because the simple example is, if you take step function of x, we can integrate step function of x, but the step function is a discontinuous function, and tan x is discontinuous for many points on the interval you have taken, but we are integrating tan x, right? So we have so many controversial examples are there. So we cannot assume like that always. So we need to find a good example for the counterpart. Yes, that's what I am saying. Cos x and sin x, if you take modulus, so it is not Riemann integrable. That's I agree. But these are bounded functions, right, on the interval what you have chosen. Cos x is a bounded function, sin x is a bounded function. So here the conclusion comes that the modulus of every bounded function need not be Riemann integrable. That is taken for granted. Here? Fine. If the modulus is a continuous function, then obviously it is Riemann integrable. That we can take it for granted, because we have a well-known result that every continuous function is Riemann integrable. We cannot deviate from the theorem. right? So earlier we have taken some of the points that one point is if the function is continuous, then it is Riemann integrable. Second, if the function is monotone, it is Riemann integrable. Third, if it has finite points of discontinuity, then it is Riemann integrable. And other one is if it has infinite points of discontinuity and they have a limit point, they have finite limit points, then it is Riemann integrable. So you have four important results. Please understand that whenever a function and an interval is given to you, these results are useful in verifying whether the function is Riemann integrable or not. It is not mandatory that whatever the function you have considered, it must follow one of these things, right? So however, we will have a discussion that now let us take that on closed interval 0, 1, you take the function f of x is equal to modulus of x minus 1 by 2. Right? Now, is this function monotone on the interval 0, 1? Is it increasing or decreasing? It is neither. It is neither increasing nor decreasing, right? If you take the function x minus 1 by 2. Accept it. I have taken closed interval 0, 1. I have taken the function as f of x is equal to modulus of x minus 1 by 2. Okay. Is it an increasing function or decreasing function on closed interval 0, 1? So if you draw a graph, up to 0 to 1 by 2, you draw the graph of x minus 1 by 2. It will be decreasing. If you take x value from 1 by 2 to 1, if you consider mod x minus 1 by 2, it will be increasing. Yes or no? Right. So it is neither increasing function nor decreasing function. So this function is an example for it is not at all a monotone function, but you know that it is a continuous function, hence it is Riemann integrable on closed 0, 1. So this example states that it is an example for that the function which is not monotone but Riemann integrable. Okay? Is that clear? So if you want to give an example give an example of a function which is not monotone but Riemann integrable. Infinite discontinuous points and having finite limit points, right? I will elaborate that point. So for this, we have already done a problem. So while discussing about the continuities and discontinuities concepts, we have a problem that we have defined f of x like this. Can you remember this problem? It was defined like this earlier. The function is defined like this. Can you recollect that problem once? All of you? Please check on the problem. You have the notes of previous sessions with you. and we have proved that the function has so many discontinuities 1 by 2, 1 by 2 square, 1 by 2 cube, 1 by 2 power 4, so on. All these are nothing but the points of discontinuities for the function. Say, can you recollect or not? Please tell. Can you recollect that problem? How it is defined? The function is defined on closed interval 0, 1 as f of 0 is equal to 0 and f of x is equal to 1 by 2 power n, where 1 by 2 power n plus 1 is less than x less than or equal to 1 by 2 power n, for n is equal to 1, 2, 3, so on. Now, if you want to write the function, it will come like this. Accepted? The functional criteria. Right. Now, what are the points of discontinuities for this function? 0, 1 by 2, 1 by 2 square, 1 by 2 cube, so on. These are nothing but the points of discontinuities for the function. Because at 1 by 2, if we calculate right limit as well as left limit, they are unequal. At 1 by 2 square, if we calculate right limit as well as left limit, they are unequal, and so on. So the limits are existing and they are unequal, so it has jump discontinuity at these points 0, 1 by 2, 1 by 2 square, etc., etc., etc. So how many points are there? These are infinite in number. So it has infinite number of points of discontinuities. But for the sequence of these points, what are the points of discontinuities we have mentioned? These points have a limit point. Because limit n tends to infinity, if you apply 1 by 2 power n, it is nothing but 0. Accepted? So the function has infinite number of points of discontinuities, and if you take all the discontinuous points as one set, it has a limit point, it is nothing but 0. Agreed? Yes or no? And even though in this criteria also the function is Riemann integrable. So just forget about the word Riemann, it is nothing but the function is integrable. What does it mean? You are able to evaluate the integration value of the function. That's it. So how I am going to do? I am going to evaluate the integration here. So I am going to find the value of integral 0 to 1 f of x dx. It is nothing but limit n tends to infinity integral 1 by 2 power n to 1 f of x dx. Agreed? Yes or no? So I just want to find the integral part of this thing. Then if I apply limit n tends to infinity, I will get the integration value. So my intention is I am going to calculate 1 by 2 power n to 1 f of x dx. How the value is going to come? So it is 1 by 2 to 1 and so on. You will get the value as accepted? Please check on the bifurcation part what he did. Agreed or not agreed? Right. So we are going to substitute the function values there. This is integral 1 by 2 to 1. Here the value is 1 dx. So I have taken these values as per the bifurcation is considered. Now I am going to integrate the values. Here the integration is 1 into 1 minus 1 by 2. Here the integration is 1 by 2 into 1 by 2 minus 1 by 2 square and so on. And I am going to simplify the value. I will get the final value as 2 by 3 after applying the limit. However, I will give the posters for you. You check it in Telegram. It is just doing the integration part. Right? So this is a good example that even though the function has infinite number of points of discontinuities and all these discontinuous points have finite number of limit points, then the function is Riemann integrable. In other words, you can say that it is a piecewise continuous function. So if we take the whole interval, the function is going to be continuous segment wise. So there are some points of discontinuities within the interval. That is the whole idea behind it. Okay. The four conditions what we have just stated are the definite conditions. If you are able to prove that it is continuous, then it is Riemann integrable. If it is monotone, Riemann integrable. If it is a constant function, Riemann integrable. If it has finite points of discontinuities, Riemann integrable. Infinite discontinuities with a limit point, then it is integrable. These are the definite conditions. That's why they are nothing but the theorems. So if you are able to prove that the function and an interval, they will come under one of the four categories what we have stated earlier, then the function is Riemann integrable. Okay? Right. So let us wind up our discussion here. Tomorrow we will meet with other concepts of Riemann integrability. So mostly we will wind the discussion on tomorrow, or we will take one more session on Monday with regard to Riemann integrability. There we will conclude this part and we will start a new chapter. And in the meanwhile, I am going to plan a small assignment for you with regard to differentiation. And you have learned about mean value theorems like Rolle's theorem, Lagrange's theorem and Cauchy's mean value theorem. I want to give some practice problems on it, and I will give some problems on continuity also. Because you have done it a long back, it will just become a refreshing one for you. And whoever has a doubt with regard to the infinite series assignment, you just give the questions on a paper and we will give the necessary solution to you. You can check on that. Because once you have the solution, the clarity will be given to you. Riemann stages is not in syllabus. There is no need to prepare for that. Only Riemann integrability is there. The thing is, initially Riemann has developed so many concepts for the integration, and stages has modified that. It's a different issue. Stages concept. So our discussion is confined with Riemann integration only, not for Riemann stages integral. So that's all for today. We will meet tomorrow with the other concepts of Riemann integration. And you just check within 5 minutes, I will give you posters of it. The problems what we have discussed. Right. Is the discussion sufficient for you, or you need any elaboration after this? And do we need to cover something more on some areas? Okay, fine.